because nobody really did anything. It's just that it's good. We want to be nice to kids. So we want to kind of suspend our disbelief and say, yeah, anybody can cure cancer. Why not you? Okay? But generally what people who are doing, getting into this kind of an area from there would be essentially, they won't necessarily know loss functions or computing, gradients, etc. It turns out they're all done behind the scenes for them. Imagine if people flying the flight planes actually need to know aerodynamics. Right? It's part of civilization is to let even people who are impatient get things done. And so in this area what happens is the actual gradient computation, even though I'll show you once today how to do it, it's normally done in an automatic way in what's called the automatic differentiation. Okay, and by the way, this computation of gradients, especially in these kinds of structures, using chain rule, has been given a very fancy name. It's called backpropagation. Okay, and the strangest thing is that particular idea has been quote unquote invented about 18 times. And the last guy to invent was Geoff Hinton, who is very, very upfront about how he got most of the credit. Because the other ones were not read carefully enough. This time he published it in Nature. Remember Nature I told you? Should always publish in Nature. And he knew that if he publishes it in Nature, some psychologist will read it. He also knew that Nature will only take the top guys in that area. So he knew that there was this one guy in Oxford who will get this paper. So he bought a ticket, went there, talked to him, convinced him about his paper. And the rest is history. By the way, he says this himself, he's pretty upfront about it. He doesn't remove any of his great contributions. Sometimes the great idea comes many, many, many times. Okay, so backpropagation is not even a great idea, it's just obvious. But obvious ideas are the hardest ones to take seriously. Because who would ever believe that chain rule, if you go tell your mom or dad, I'm getting like AI job, and I'm going to use chain rule, right? It's so bad. And in fact, at one point of time, I used to think when I was teaching this Google, this information integration course, that people can increase students' interest in linear algebra, which all of you go through, sort of saying, why the heck are we doing this? If only they told you, PageRank that Google uses is just an eigenvector. I thought, wow, Google is using it. Let me understand what's going on. At least I want to kind of learn some buzzwords. And similarly, differential calculus, the long-suffering teachers in the high schools who try to teach kids differential calculus, if only they tell them, differentials are what are used in deep learning. And read up your New York Times. I think they're telling because that's why I get all these emails from students saying we also want to do research. It's a great way to understand that gradient descent, which basically involves chain rule application, which you learned long, long back. Remember, differentiation is not even the hard calculus, right? I mean, even those of you who hated calculus, that differentiation was for the birds. It's the integration that kills you. Do you understand what I'm saying? There is no auto-integration. There is auto-differentiation because it's plug and check. So in fact, just like there are spelling bees in the world, in some nerdy schools such as MIT, there are integration bees. They don't have differentiation bees. You see what I'm saying? There's no point. Differentiation is a science. Integration is an art form. You can either think of it as a good way or bad way of saying things. Scientists look at something that's not been fully, rigorously formalized and say, it looks like art. Okay. In some sense, art essentially means we haven't automated the heck out of it. If we understand exactly how things work, we should be able to write a program. That should be it. You see what I'm saying? Integration, we still are not there. Differentiation, that ship has sailed long back. And in fact, chain rule-based differentiation, which is the backpropagation step, it's not surprising. That can be easily automated. We will give you an idea towards that after this class. Okay? So that's basically where we were. Okay? So I also talked about loss functions. I talked about different kinds of loss functions. And I mentioned cross entropy loss, essentially, we will talk about it in more detail later again, but as I said, it assumes that there is a true distribution T and there is the distribution that is actually being given by the network. So the numbers that are coming out of the perceptron, if it's using the logistic function, will be between 0 and 1. If they're between 0 and 1, it's a probability distribution. Especially if there are two values, and one value is between 0 and 1, then the other value is 1 minus that. It's a probability distribution on a 2RE. It's a binomial probability distribution. You can actually have multinomial logistic functions, in which case you will essentially have multinomial distributions which are being compared to other expected multinomial distributions. Do you see what I'm saying? Okay? So in fact, that brings up, so if you are doing this, then what comes out is a number which you can interpret it either as if it's more than 0.5, I meant to say it's 1, if it's less than 0.5, I meant to say it's 0, or you can say if it's 0.7, I mean that it is class 1 with 0.7 probability and class 2 with 0.3 probability. Now, if in fact you happen to know, because this is all supervised learning, which by the way means that there's training data whose labels are known, and suppose this particular example happens to be from class 2, then the true distribution is 0, 1. Because it's class 2, so its distribution, true distribution is its probability of belonging to class 1 is 0, probability of belonging to class 2 is 1. So you are comparing the distribution 0, 1 to the distribution 0.7, 0.3. That's what cross entropy loss basically does. And so there are distances defined for distributions, called, one of them was called K divergence. And cross entropy loss is basically derived from there, and this is how it looks. This is how it looks. The only interesting thing is because previously the derivative depended on the loss function when it was 2 error square, the first thing you got to do is 2 error square becomes 2 times the error when you take the differentiation. And the 2.5 get cancelled, you'll be very happy. Right, remember that? Now it won't be 2 error square, it's not square at all. It is minimization of the sum of the cross entropies. The huge number of logs floating about. You see what I'm saying? Okay? Of which, by the way, which are variables and which are constants. The Q's, the outcomes are variables. The T is the true distribution. If I said this example belongs to class 2, then the distribution is 0, 1. If I said it belongs to class 1, it's 1, 0. If it's a multinomial distribution, there are 15 classes, then it's 0, 0, 0, 1, 0, 0, 0. That would be the distribution. And then your perceptron might give some set of 15 numbers, they're all positive, and they add up to 1. And you are now computing the distance between these distributions, and you are minimizing them. It turns out that there basically the differential, instead of depending on 2 times error, will be slightly more complex. Okay? And then of course there is also the threshold function, you need to have the g dash of that, which for logistic regression, logistic function we know basically has this nice property. Remember that if you have g of x equal to 1 by 1 plus e power minus x, g dash of x can be shown to be this. It just happens to be. Okay, so this much we have done, and if you want to apply, as I said here, if we use a perceptron unit with a sigmoid function as the thresholding function and cross entropy as the loss function, then perceptron training gets us one of the great ideas in machine learning from statistics, which by the way, statistics basically tries to solve the same problem machine learning tries to solve. Except statistics is not particularly, sexy, right? Plus, they don't know how to start Python. They depend on that's the difference, essentially. Right? But statistics is actually very well connected. In fact, we will talk about the only theory for learning comes from statistics. And we will talk about it. Right now we are just going in terms of minimizing error, etc. We can give much better reasons as to why learning is supposed to work later on. But anyway, from statistics, this idea called logistic regression was around. Lots of people have been using it. Now, the interesting thing is, how many of you have heard deep learning before coming to this class? Raise your hand. Okay, put down. How many of you heard the phrase logistic regression before coming to this class? Wow, very good number of people. But still smaller. That actually was the list, Kaggle basically looked at the actual learning algorithms people were using on the Kaggle competitions. This was 2017, I tried to look for the latest, I couldn't find any. They actually surveyed people, some 7,000 people, 10,300 people, and then they looked at it. Notice who was at the top. This was 2017 is just as crazy hype about deep learning as it is now. And yet, essentially, logistic regression was being used, on many kinds of data. Okay, and it's connected, of course, to the neural network learning, but it's really a much simpler kind of an idea. And another thing that was being used, by the way, where is neural networks is here, right? And there's another idea called SVMs, support vector machines, that I discussed in the videos that you're supposed to have seen, and there's some very interesting discussion that was going on in the class between a couple of people. I gave an answer to that too, which we'll talk about in a minute again. Is also being used. And by the way, the CNNs, RNNs are also actually neural networks. I don't know why they differentiate it. But in general, it's interesting to know that for many problems, logistic regression is what you should try first. Okay? But then you can tell your boss, and the boss will say, no, what is this logistic regression? You look like one of these statistics beats. I thought I got a real computer science guy. Then you say, oh no, I did deep learning with cross entropy loss function, sigmoidal error function, and no hidden layers. Say extremely low value. Right? You'll be fine. You'll keep your job, and then somebody else will lose theirs. But anyway, so that's what to keep in mind. So here is something that I mentioned last time, and I'm going to say it again, which is, in general, when you go through all the steps, in many use cases, the gradient descent update equations would look like this. The weight Wi for this perceptron, let's say, is going to be updated in terms of the gradient of the error function with respect to this particular weight. It really should be dou, but since I'm writing in PowerPoint, I wrote it. It's unfortunate. Okay. Right, so it should be like this. Right. E is the loss, which is the error, and the threshold function is basically going to be in the G, and the actual ith input value is II, and the form of the update itself depends on the input, the differential of the threshold function, and the differential of the error function. For the square errors, the differential of the error function typically will be II minus OI. You see what I'm saying? So that's basically what we're going to keep in mind. And so the question, of course, is, since perceptrons with logistic regression seem to be kind of a nice idea, and we're looking at classification, do they solve all problems? Obviously, by now you know that perceptrons don't solve all problems. But put yourself in 1962, when this guy from Cornell, Rosenblatt, was going around giving talks, saying, I have this. In fact, he even implemented a perceptron. You should see some of those perceptrons. They look. Obviously there was barely any reasonable computers in the 60s, right? So it will be a room-size perceptron chugging away, right? And it will actually sort of solve interesting problems. By the way, I wish I had that slide here. Let me see if I have. One question that I should mention before we go off, this one, is this. People have asked this question. I mentioned multinomial classification problems. That means multi-class classification problems. It's not yes or no. It's this is the data that you've been given is from one of 15 categories, and you have to guess which category it is. That's a very useful thing to do. which is where I said the distribution will be, the true distribution will be 0, 0, 0, 0, 1, 0, 0, 0, 0, a total of 15 numbers. And the computed distribution would be some arbitrary set of numbers adding up to 1. Right? And solving this problem is more useful than solving binary class classification problems. But you can use perceptrons for multi-class classification problems. And it doesn't increase the complexity of perceptrons. What you wind up doing is the same inputs are being fed to, if there are 15 classes, there are 15 output units. Do you see what I'm saying? So in a sense, you're using the same inputs to train 15 different output units. This is looking much more complex than this guy, which you have seen and loved. There is no difference. It's still a linear perceptron. And it's not deep, because it's a single layer of nodes. You see what I'm saying? There is no hidden layer in between. People asked, and it's a very reasonable question to ask. And in fact, it's these problems, applying logistic regression to multinomial classification problems, is what got people taking machine learning seriously. Right? Okay. So, and people understand that this is still linear perceptrons. It's just that you are, and you can essentially compute for each of these outputs. It's basically what you're doing is, if you're, for example, trying to compute the root mean squared error instead of the cross entropy, right? You can still do that. Where in every place, if it is the correct class, I mean, you know, if it's, let's say the example that you have is the last class. Then if this guy says the example is 1, this unit comes out as 1, okay, then 1 minus 1 would be error 0. If not, it would be whatever the error is. And you are essentially summing the errors and minimizing it. In general, actually, for multinomial classification, people use the class entropy. They don't use the square error. But the idea is the same. Okay, so let's go forward. Many times I think you can go back and watch his videos and stuff. But anyway, so the question is, look, perceptrons are doing pretty good stuff. They can do multi-class classification. So this is where, you know, our man Rosenblatt was going from place to place saying, wow, I solved the world. You know, this is like sort of saying, remember there was this old story that when Archimedes, did I mention the Archimedes story already? When Archimedes, you guys know Archimedes, right? And his Eureka movement and running around naked. Yeah. The kind of stuff all of us want to do. Yeah. But one of the things, the reason he basically was saying Eureka is like, that story is slightly different, but one other thing that he learned was, he learned the principle of lever and fulcrum. Okay, so if I have a big enough stick, I can lift this particular desk by essentially putting a fulcrum and put the long end of the stick on my side and then lift it and it will lift. Right? And so having done this, in fact, there is a story that when some arbitrary people came to take over Athens, they kept their ocean-going ship outside and they just let him do whatever the heck they wanted. They haven't yet learned in their grade school that there is this thing called principle of lever. So as they were hanging around in the ship, this guy put a huge big lever, put a fulcrum, and then just lifted it. And the ship fell down. That's how he became popular. Not for running around naked. This is the real reason he became popular. And I always think of good old days where people will allow this guy to build an entire fulcrum and get a huge big lever and say, oh, it's all completely fine. You know, what can this guy do? Probably he's naked, whatever. But the thing is that having found this, Archimedes is said to have exclaimed, saying, give me a long enough lever and a fulcrum, I will lift the universe. I will lift the universe. Not Earth, not moon, the universe. Right? Whoever comes up with a good idea thinks, man, that idea, I can just do that. So Frank Rosenblatt was saying, even if big enough, wide enough perceptron, not deep enough, but wide enough perceptron, I can solve any machine learning problem you have. Then, so enter the spoil sports called Minsky and Papert. Marvin Minsky is one of the 4 people who was in that 1956 conference that started the AI, because they had this conference named after, it's been named Artificial Intelligence Conference. So anyway, they asked a simple question. They said, I understand you can solve all sorts of problems, different kinds of multi-class problems. Can you just solve all Boolean functions? Think about this. What is a Boolean function? Suppose you have a Boolean function I1 and I2, and so I1 and I2 are the Boolean variables. Remember the Boolean algebra, right? Okay. And if I want to define I1 and I2 as the function that I have in my mind, right? Then this would be positive, all these 3 will be negative. Can your perceptron learn this? Of course. Hey, right? Good job. Okay. How about I1 or I2? Absolutely. How about I1 XOR I2? Oh, leave it to spoil sports like him to figure out things like XOR. Who shouldn't be asking about XOR? We are happy with and it's not us, right? So XOR, you know what is XOR, right? It's exclusive OR, where it's just like OR. OR is basically if any one of the variables is positive, the OR is positive. Otherwise, it's negative. That's why you have 3 black dots, 1 white dot, and a nice little line you can draw. So then they said, okay, let's try to do your thing on an XOR function. What is an XOR? It will have, if I1 is 1 and I2 is 0, it will be 1. I'm sorry, I1 is 1 and I2 is 0, it will be 1, and I2 is 1 and I1 is 0, it will be 1 again. But every other time it will be 0. Now can you draw a line? Well, of course, if they showed this to Frank Rosenblatt, he too could have said, of course, this can't be done. But they put it under some random thing and say, you come up with a big problem which has an XOR in the middle of it. Screw. It's like building your amazing, whatever, the Star Trek thing, the Star Wars thing, and putting that little pole, right? Okay? So XOR is the way you can kill this guy. So they wrote a book. I mean, this is the kind of thing, not just, you don't just kill somebody, you kill, as one of my friends says, when you kind of step on an insect, you do this. So until it really hurts the insect. That's the kind of thing that Minsky and Papert did. Not only have they pointed this out, they wrote an entire book. You would think, how long can you write this book? The first 2 pages, stuff is over. Basically, nobody read after the first 2 pages. And in the first 2 pages, they said XOR is going to be the Achilles heel of neural networks. And they said it would be fine if you go to multi-layer networks, but nobody needs that stuff. And then people will say, extra, read all about it. Neural networks are dead. And basically neural networks are dead. So in fact, you should go back to New York Times archive and look for perceptron articles. If you remind me, I will show you and send it to you. They had basically, that was like one of the earliest crazes about AI. And then it died because this guy said, hey, you can't do Boolean functions. What? It's 1960s, 62-ish type. Okay, now here's the interesting thing. What about some of the other things? So in fact, you said this I1 and I2, it can be separated, but really, actually that's not the way they're thinking about it. Originally they start, let me just come with a neural network. And here is a neural network that works for AND. You can put I1 and I2 here, the W's are ones, and then the bias, which is you add the W1 times I1 plus W2 times I2 minus 1.5. And then you take a step function. That will work as AND. So here is an existential proof that there is a neural network that solves this. But you don't need this if you saw this. But this is hard-won knowledge. Now we know. But at that time, basically, people were trying to build the neural networks and saying, hey, it's not working. I would say that in sort of some of that stuff is happening right now too, but right now suddenly it was happening then. And then so in fact this is AND, this is OR, this is NOT. You can't come up with a network like this for XOR. What does that mean? You can come up, but it will have a large error. It will most of the time be wrong. Like half the time it will be wrong. And that's no good. Do you see what I'm saying? So basically the loss function, if you looked at those videos, the loss function never goes to 0 for the perceptron. Okay? Now, you guys did Boolean algebra. You know XOR, for example, you can write any Boolean function in terms of ANDs and ORs and NOTs. Right? So here is actually a neural network that does XOR. Why doesn't this disprove what I've been saying? Because it has a hidden layer. And it's that hidden layer that would be needed. And one of the interesting things is at that time, one of the points that these guys were stuck on was for the perceptron itself, if I can find that picture. Okay. For the perceptron itself, the error surface would be convex, which means it will only have one minimum. Which means even if you computed your gradient wrong, you will fall into the minimum. You see what I'm saying? It's like if you are not a particularly good mountaineer, and you can either go up Mount Whitney or Mount Fuji, geographic quiz. Which one would you pick? Mount Whitney or Mount Fuji? I mean, if you should know when you reach the top. Or Mount Kilimanjaro or Mount Whitney? Or Everest or Mount Fuji? The question is not one of endurance. The question is, do you know you have reached the top? For the longest time, in fact, Fuji, Kilimanjaro, these are all volcanoes. That's why they're so damn beautiful. Everything else is flat and shoop, it raises. You need to be particularly stupid not to know where Mount Fuji is. For the longest time, people didn't know Everest was the tallest peak in Himalayas. If you go to Himalayas, Everest is never obviously the tallest. Do you see what I'm saying? In most places, things like Makalu will look much more impressive. Do you understand what I'm saying? Okay? So, a volcano is a convex peak. Around, in its surroundings, there is nothing. So people who just say, I just want to increase my height, like this. And then when I take next step, I'm coming down, I say, I have reached the top. Just like Columbus saying, I have reached America. Okay? And Columbus would have been right if in fact, Columbus said, I reached India. Columbus would have been right if there was no America. You guys put this America thingy in the middle. There really should be only Europe and India. Things would have been much more interesting. For one thing, we wouldn't have had this class. Right? But anyway, so the point is that they were looking at these convex functions where pretty much any random gradient descent will be able to find the minimum. Just as even a blind man, a blind woman can go up Mount Fuji. Because they would know when they have reached. Mount Whitney actually is extremely hard to tell that it's the tallest, either it's the tallest peak in the continental United States. Mount Whitney. And of course, and it's basically, it's very unimpressive because it's not a volcano. So it's like, most people won't even know until you get to the highest obvious peak and then say, oh, there's something more on the side. What that means is there are multiple maxima in the mountaineering terms. And in the search terms, there are multiple minima. And the biggest worry people had is since gradient descent is a local search, how the heck can it find the local minimum? How the heck can it find the global minimum? The answer is, it still can't. It still can't. But we don't care. Because after all, we will find whatever we find and say, that's India. Neural networks are doing this every day. They are finding India every day. You see what I'm saying? There is no guarantee that they have found the optimum on the error surface. Nothing like that. There is no such mathematics. The only way you can find the optimum in a complex error surface with multiple local minima is to actually, in fact, there's no way, essentially, because you have to find all the local minima and find which is the biggest. That's basically impossible to do. So instead, people focus, whenever machine learning people are worried about, well, will we ever reach India, will we ever reach the only minimum? They will say, how about changing the globe? Remove America, then you will reach India. How about changing the error function such that the error function is guaranteed to be convex? And if it's not convex, you will say, oh, that's not machine learning problem. I won't solve it. And I can't be wrong if I don't solve it. You understand what I'm saying? If I refuse to solve it, I can't be wrong. Okay? That's what was happening for most of the time. In fact, it was happening until 2006, 2007, 2013 time. And as I mentioned last class, it seemed to be not as bad as you would think, either because we don't any longer care, we are just as happy if something looks like a dog and we say it's dog. Every time a school bus becomes an ostrich, we'll say, that's a little error. But then we'll keep on using this stuff. And then we use this on our x-rays, and people are doing operations on us, thinking we are school buses, I don't know. But either which way, we are sort of given up looking for optimal. But there is also a positive way of looking at this, which is that, in fact, there won't be too many bad local minima in a very high-dimensional space. Remember, I spent an entire time talking about it last time. This is stuff that can be talked about now. It wasn't known at that time. So basically, these guys said, look, you can't even do the Boolean functions. How the heck do you expect to do anything more? Okay, and people start working on neural networks. Okay, there are two ways to handle this, which you have seen if you look at the videos. Okay, one of course is transform the data into higher dimensional space, and then if in fact you have n points, n training points, okay, and if you make, n training points, let's say, of 3 dimensions, okay, that means x, y, z coordinates. If I now invent n dimensions, x1 all the way to xn, that means every point has its own axis. It's like you are unique, you have your own axis. You can see that in that case, there will be a hyperplane that separates any class from any other class.